First, it's asking us about the tangential speed of an object at a specific orbit. So let's recognize from the beginning that to be in orbit is a bit of a balancing act, a ballet, if you will, between your speed at which you're falling and the orbital velocity that you have. Meaning you're moving this way while falling this way. We're trying to balance those things so that you are more or less falling around the planet. And although I've used those phrases before in discussing this, what I really want to remind you is that there needs to be an unbalanced force that is matched by your orbital parameters. That has to include how fast you're traveling and the radius of curvature, in this case the distance from the center of your turn to where you are traveling in that turn. Now, it doesn't matter which side we look at first. In any circular motion problem, this is what it takes to make that circle. This is what is causing the change in your direction. So that's always going to be the case. So let's take a look at specifically an orbit. An orbit is when gravity is what is causing the change in direction. So the left side of this, the net force, is from gravity. In this case, you're orbiting the Earth, so one of the masses has to be the Earth. The other mass has to be, in this case, the space station. G is just a proportionality constant. It's going to be there every time. And then there's the separation distance between the center of masses. Here's where a lot of you made your mistake. That distance is from here to where the other mass is. I didn't give you that distance. I gave you the altitude, 150,000 meters. Altitude is from the surface of the Earth. You would have to add the radius of the Earth, 6.38 times 10 to the 6th, to the altitude to get the actual separation distance. That's where a lot of you made your mistakes. So the actual distance is 6.53 times 10 to the 6th meters. That's the distance from the center of the Earth to where the space station is. A little wrinkle. And don't be thrown off too much if you didn't catch that wrinkle. But, no doubt, deep down inside, I was laughing at you. At the same time, the right side of this relationship has to do with what's in orbit, what's going around the planet. And that is the space station. It's important to get this part right because one of the masses in an orbit is likely to cancel out the mass of the object in orbit. Yes?
For the distance between the center of the Earth and the space station, what's the exponent to the 10? I can't see.
To the 6th. You're just adding those two things together. So 6.38 times 10 to the 6th plus, 150,000. All right, moving on. Mass of the satellite times the tangential velocity squared divided by r. Now, I'd love to tell you that these always play out the same way. They don't. It really depends on what is being asked of you and what you need to reply. But in this example, we were specifically asked for the velocity of the object in orbit, which means I can cancel out the mass of the space station, and I can cancel out one of the r's, leaving me the mass of the Earth times g over r equals vt squared. Let's take the square root of both sides. Now you got to put the big numbers in there and push the buttons. And as a reminder, you will not have to memorize these numbers, but mass of the Earth, 5.97 times 10 to the 24th. G, 6.67 times 10 to the negative 11th. And R, in this case, 6.53 times 10 to the 6th. Now, even if you had used just the Earth's radius, you wouldn't have been off by much. But if you used 150,000, you would have been off by a lot. Order of magnitude. So, tangential velocity, 7,809 meters per second. The hard part, I think, here is that you have no idea whether this is right or wrong. The number you got might as well have been, a mystery. I mean, it's hard to frame this. It's hard to know whether 7,800 is close to the right answer or not when you have no experience. That's why some of the other problems we've done, we tried to base it on things that you would have known about, like the Earth going around the sun or the moon going around the Earth, something where you could get an answer and check it against reality. This is right. This is how fast the space station has to be moving, which is exceptionally fast. It's hard to fully appreciate how fast this is, except to know that we can't make anything go this fast inside the Earth's atmosphere without it burning up. The fastest something can travel in the Earth's atmosphere and not explode on its own is just under 5 times the speed of sound, which is about 1,500 meters per second. This is why there's a heat shield on everything that has to come back into the atmosphere, because it comes in when it enters at this speed, or slightly less than this. And it's very hard on the people or the things that are inside. Yeah?
So all of the radius and distances, those will be on the board, or do we have to memorize?
You do not have to memorize any of these natural constants. Now, it is plausible that I could give you other information and ask for you to solve for one of these masses or one of these radii. As you could see, this problem could be done just as easily if I told you that the orbital speed was 7,900 and asked you to figure out what the mass of the Earth is. It's the same problem, just a different unknown. So, but no, you would not have to come in with any of these memorized. Any of the physical constants you would be provided. All right, that's question A. If you get question A, you are very likely to get question B, which ends up being I think it's 87 minutes. But if you didn't get A right, you couldn't get B right either. Just to make sure we're all on the same page on that, question B asks for the orbital period. And the orbital period is how long it takes an object to go around that orbit. And just as a reminder, that probably has to do with something like how long it takes to go around a circle being related to how fast you're traveling around that circle. If I want the period, I can just solve for it. The problem is that your answer's in seconds. You're asked to place your answer in the most useful units. Minutes is useful there. 87 minutes is appropriate. If you decide to go hours, though, be aware I do not want a decimal point for hours. Convert those decimal points into minutes, something appropriate. So if you decide to go to hours, don't give me 1.3 hours or something like that. Give me 1 hour and something minutes. All right. Question C has been asked quite a bit today. And so that's where I was actually starting this problem. But it's not nearly as difficult as it sounds. If we assume that the space shuttle is going to reach the speed of 7,809 meters per second and do so in 11 minutes, which is 660 seconds, probably if I know the initial velocity, I could figure out the acceleration, assuming constant, because I could use a motion equation to do so, assuming constant. Now that's important to understand. The actual space shuttle and most rockets do not make a constant ascent. They change it all the time. If they ascend at a constant, they go too fast, too early, and burn up. So they tend to go slow in the beginning and then speed up later. Either way, this actual answer is going to be very dependent on what you decide to put for your initial velocity. If you've been paying attention, you know that we are not sitting still here at the equator of the Earth. We're moving, right? We go around the edge of the Earth once every 24 hours, which gives us a speed of about 400 meters per second. If you had remembered that, and put 400 meters per second here, or whatever the actual value is, I'd probably be willing to give you credit for knowing that. Like extra credit, because that's pretty intuitive. I think most people who do this problem simply assume we start from rest. If you assumed you started from rest, you'll get 11.8 meters per second squared as the acceleration required to get into orbit. Not too bad. Very endurable. Most of you can endure that with no trouble at all. Now, enduring it for 11 minutes might be uncomfortable, but definitely not too much. Yep.
Do we have to memorize those motion equations for the test tomorrow?
You're allowed to. At this point, question D is another motion equation problem. It just asks for the displacement. I would have used 1/2 V initial plus V final times time. How far do you go while you're accelerating? Really wasn't much of a stretch. 2B and C. It's funny because this actually was a point of consternation in fourth period today. But I do want you to know I do not have a formula for this. And I would not expect you to have a formula either. I would expect you to be able to figure this one out. So, but part of the reason for having it on the practice test is so that you could have seen what I would expect you to be able to figure out before the actual test. Does that make sense? So, just so we're all on the same page, question A actually asks for the maximum available frictional force. It's 0.04 newtons. If you didn't figure that out, then you're not paying attention. But static friction is less than or equal to mu times the normal force for a coin that is sitting at rest. There is a weight downwards, normal force upwards, and if there's friction, it's going to be to the side. The maximum available friction would be from mg. Mass is 10 grams, not 10 kilograms, which is why your answer of 40 newtons is wrong. It's 0.4 times 0.01 times 10, or 0.04 newtons. That's the maximum available frictional force. You'll need that for question D. But question B and C are the same question, so I'm not going to do it for both. I'll do it for one. It says that how fast is a point on the edge of the record moving when the player is set for 33 1/3 RPM? I am amazed at the number of people who know what records are. I am less impressed with the number of people who've actually seen one and know anything about them. I like records, though. I lived in a day when those were around. So we're looking at how fast is a point on the edge going when the whole platter is traveling 33 1/3 RPM, which, by the way, not everybody is able to figure out that 33 1/3 RPM is 33.3 RPM. It's one. You're just adding a third to 33. So let's start with that and what that really means. Again, I have no equation here. 33 1/3 RPM is 33.3 rotations per minute, which is 60 seconds. Any question about where I came up with that? Because I didn't make that up. It's not an equation. I'm just rewriting what they say. You sure? All right. Well, a rotation for a point on the edge is a circumference. It's making 33.3 circumferences every 60 seconds. 33.3 times 2 pi r every 60 seconds. That's it. That is the velocity of a point on the edge. You put in r. I will also point out that 33.3 times 2 pi over 60. If I put all of that in the front and put r afterwards, this kind of tells you that depending on where you are on the record determines how fast you're traveling. This part is what the entire record is doing Every point on the record is going around one circumference 33 times in 60 seconds. Every point on the record's doing that. So if I am at the edge, I would put the radius of the whole record in. If I was here, I'd put in a different number, how far away I am from the center. It should be pointed out that if you're at the center of the circle, you have no tangential velocity. R would be 0. So you can write an equation that kind of tells you what your linear velocity is based on how far away from the center you are. That's what this would be. Did I make it up? Not really. It's right there. If I want to do this for 45, I would just drop 45 in for 33 1/3 and do it over again. Either way, I believe the answer worked out to be, actually, I don't remember, 4.1 maybe? I don't know. You guys work it out. You do need to know, no, it's actually less than 4.1. It's much less because the radius is 0.155 meters. First, people forgot to put it into meters. Second, they didn't realize that I gave you a diameter. You have to cut that diameter in half. So 31 centimeters is 15.5 centimeters. 0.54? All right. 0.54 meters per second. That's how fast the point on the edge is going. If you couldn't do that part, you really probably couldn't do question D. Question D isn't particularly hard, but it's not straightforward. Question D asks, where can I put the dime on the record and not have it slide off at each speed? To me, this is an excellent test question. Brings everything together. So let's talk a little bit about what you'd have to do for that. If I don't want it to slide off, then I need to remember that this balance will have to be struck. I have a limit to how much force I can have. It's coming from friction. So if this is my record and my coin's being placed somewhere away from the center, it's going to have a tangential velocity that's dependent on how far away from the center it is. More importantly, the force that's holding it in place is friction. Friction's holding it in place, which means that I have a finite maximum amount of friction available. That's what you solved for in Part A. That's why Part A exists in the problem, to help kind of chime you into that. This is causing my mass of 0.01 kilograms to travel in a circular path. Here's the problem. This side tells me that the acceleration that I experience is dependent on how far away I am from the center. But I just figured out that the velocity is also dependent on how far I am from the center. That's tough. That makes this problem hard. Not impossible, though. If I go back to what I found in Part B, which stated that the tangential velocity was 33.3 times 2 pi divided by 60 times r. This is a relationship for the tangential velocity in terms of how far away I am. I mean, I think all of this is like 4.3, I think. Which means I can say that the tangential velocity is 4.3 times r. I don't know that I would have expected all of this on an actual test, but on a practice test where you can talk to the person next to you, sure. So I'm thinking, yeah, I think you worked that out. Figure out what r is. 0.04 divided by 0.01 is just 4. And that equals 4.3 squared times r. R equals 4 divided by 4.3 squared. I don't know what the answer is, but I think it's like 0.3. Is it 0.3? So 0.206. That's still not the answer. Don't erase. If you did all the math right, it's okay. You can't place the coin there. The record has a radius of 0.155. So I can't place the coin over here and be on the record. Right? So the maximum place I can place the coin is still right on the edge. It won't fly off on the edge. I could place it further, but I don't have any further to place it. So the answer would be 0.155. A little trick question, just for fun. Now, if you want to do the problem again, and you should try the problem, but put in 45. Right? You're asked to do it for both, 33 1/3 and 45 RPM. So do the problem again. It's good practice for tonight. Oh, sorry, good practice for tomorrow. Do the practice tonight. All right. You know, we've talked about it before, but imagine one of these rides that spins you where you're kind of, against the wall here. Does that make sense? That's what this ride's like. That's what it's about. The first couple of questions actually tell you quite a bit of things to do, and you don't really have to know very much physics to work out the first couple of questions. It says, what is the tangential velocity of a person standing on the edge of the ride against the wall? Well, the tangential velocity is going to be based on how fast it's spinning, and it tells me that it makes one rotation every 6 seconds. All right, that's how fast it's traveling. So that means you're doing one circumference every 6 seconds. And I'm told that there's a radius of, I think, 4 meters. So this has got to be your tangential velocity. I don't know what this is, but I'm thinking it's like 4. 4.2? All right. That's our tangential speed. Question B, what centripetal acceleration do they experience? That probably word's probably supposed to be do they experience, because I don't think we have a doe here, a deer, a female deer. Perhaps there's a drop of something or other here. All right, so they have a tangential speed of 4.2 meters per second squared. Sorry, meters per second. So B asks for the centripetal acceleration. Centripetal acceleration is just v squared over r. So 4.2 squared divided by 4. That's it. So it's just a little bit more than 4. 4 watts. 4.41 meters per second squared. Question C, if they have a mass of 60 kilograms, what centripetal force must they experience? And what force from the wall is providing this? Well, question C is simply asking me to find that unbalanced force, which is MAC, or 60 times 4.41. So 260 what? 4?
Yeah.
All right. 266? 264, so 265. There, 265 newtons. This is the force. Now, just so you guys know, this is a force towards the center. Towards the center. This has to be a force from the wall. What possible force from the wall is towards the center? Normal. So this comes from the normal force. Yep. All right. Question E is going to continue on this. Oh, I'm sorry. Question D continues, and it's just asking kind of all the same. This problem is me stepping you through what it would take to actually answer it by going through every little detail. I wouldn't expect that on the test. The question D says the floor drops out of the ride, so you're going to be suspended against the wall. So here's our guy. He is suspended against the wall. We know there's a normal force this way. We know they have weight downwards, and that's mg. Question D asks, what is their weight? Well, their weight's just going to be mg, 60 times 10, or 600 newtons. But what force keeps them from sliding down the wall? Friction. It's the only thing that could. So there must be a upwards force of friction, and not just any friction. It has to be static friction. If it were kinetic friction, they'd be sliding down the wall. Static friction would keep them in place. And the static friction must be 600 newtons. Has to be balanced or they slide. So what must the minimum coefficient of friction be in order to feel stuck to the wall? Static friction has to be less than or equal to mu times the normal force. So mu has to be equal to mu has to be greater than or equal to the static frictional force divided by the normal force, or 600 divided by 265. I see a problem. Do you see a problem? If you don't, mu has to be greater than or equal to what? 2 point what? 3 point what? 2.2. Do you see a problem with this coefficient of friction?
Yeah.
It's greater than 1. So unless I glue you to the wall, you're probably not going to be able to stay suspended against this wall. I have a feeling that the ride is just spinning too slow, which means the floor drops out and you drop with it. I wouldn't want this ride tipped sideways. Next it says, prove that this minimum doesn't depend on the rider's mass. It doesn't. If we look back here for just a moment, take that over here. The normal force came from m v squared over r. Right, that's where we got the normal force from. And the frictional force came from mg. Do you notice this? That the m's would have canceled out? So the coefficient you choose would be effective for everybody. The reason people don't stick to this ride is because they don't spin it fast enough. We need the bottom number to be bigger, so I need to spin it faster. Or make the radius smaller. Now, you can do either one of those. The problem with making the radius smaller is, A, it doesn't hold as many people. But more importantly, if you make the radius too small, people get sick more often because they're spinning more. I want you to think about it. If you make the radius smaller and smaller and smaller, it's more like the teacup ride at Disney, and less like the carnival ride. You have to spin it really fast, but you are also spinning in a circle, so you get dizzy, not just stick to the wall. And dizzy makes for vomit. So, especially in carnivals where they have lots of deep fried cheese and ice cream and hot dogs and anything else they can put in the fryer just about. It doesn't do well when you get sick. Makes for a nasty ride. All right.